Okay, I think that's good enough. So thank you everyone for coming today. Today's webinar is focused on wireless ISPs and fixed wireless networks. This is kind of a product I have a lot of experience with in past roles. About 15 years or so, I've been putting up wireless systems of various types. And especially coming to traffic, I've been kind of surprised by how little these radios are used in traffic. And so I just wanted to try to draw some attention to it and hopefully maybe inspire some applications that you didn't know were possible, and especially for more affordable radios that are used by wireless internet service providers. I know in traffic there's some specialized radios, or at least ones that are marketed that way, but really, in my experience working with both, there's really no difference. That's why often IT takes over the networking part of traffic now. But a lot of my experience is with Ubiquiti Networks. That's why I put their logo here, and I'm going to focus on their products. There are some other brands like MikroTik and Cambian that are popular as well. But most of my experience with Ubiquiti, so I'm going to focus on that. So today we're going to start with just a broad overview of what are these products, how do they work. Then I'm going to jump into a few ITS application ideas, as well as a few case studies of ways I've used these radios in the traffic industry that might inspire some ideas on your part. And then we'll finish off with a Q&A. So I timed myself yesterday. This took me about 30 minutes to get through the bulk of the presentation, and then we'll have at least 15 minutes for questions, but I'm going to try to go a little bit faster today. So let me jump into it. So if you guys don't know who I am, my name is Michael McGuire. I'm the Vice President and General Manager of Stinson ITS. And if you don't know who Stinson ITS is, we are formerly a division of Stinson Owlite, who's been in the traffic industry for 60 years. But the beginning of 2021, we broke off as a separate company, and we opened up an office. Actually, this is me in the second office here on the left. So we got this fancy new office in Woodbridge, and but we operate across Canada. So we sell a wide variety of technology across the ITS space, and we do a lot more than just selling product. We design systems, we manage projects with long-term maintenance and operation periods. So that's where kind of Ubiquiti fits into this. Often we don't sell the radios by themselves. You can get them on Amazon, you can get them anywhere, basically. They're very widely available, but we often use them as a tool when we're selling a solution. So it's a means of communication when we're trying to connect multiple products together. So what is fixed wireless? Basically, it's a wireless IP-based network. So it's a way to connect IP networks across a wide distance so that you can communicate across them, just as if you had an actual long wire that you're plugging in from A to B, but you can go a couple kilometers or 20, 30 kilometers, depending on the conditions. And these networks are either a point-to-point network or a point-to-multipoint, kind of like a Wi-Fi hotspot, or a combination of multiple ones. So if you have a really complicated network, it's a combination of those two types, but I'll talk about what those mean in a minute here on the next slide. But as far as the features, typically these radios operate certainly at the point-to-multipoint level at the 5 gigahertz range. That's the most popular. But when we do point-to-point networks, we typically use higher frequencies because you can get larger bandwidth and throughput. So the 24 gigahertz and now more recently the 60 gigahertz band is now available for license-free operation. And the other quality of these networks is that they're very long distance. So typically when we're doing smaller point-to-multipoint, you're talking about a couple hundred meters to a few kilometers. But if you have good line of sight and want to do point-to-point or even point-to-multipoint, you can get up to 10, 20. You can actually go much more, but I only have experience going about 10 to 20 kilometers at the most. And but that is quite impressive nevertheless, considering how small and affordable these things are. And these radios are also providing very high speed data rates. So on the lower end with point-to-multipoint, you're usually limited to about 10 to 200 megabits per second, which is more than enough. Typically, if you're streaming a camera at 1080p, it takes about 5 megabits per second. So it's usually all you really need for a remote connection. But once you start getting to the point-to-point networks, that's when you get 500 megabits a second, 1,000 megabits a second. Some of those you can go up to 2 gigabits per second, but yeah, that's more the heavy-duty point-to-points. but usually all you need is a couple megabits, but you get more than enough from these radios. So a little bit more information on what point-to-point, point-to-multipoint means. So point-to-point means one radio on each side of a connection, providing a dedicated, usually a backhaul link, where you just want a single connection across typically a long distance that's very high data throughput. And then point-to-multipoint is where you have an access point, which is kind of like a Wi-Fi hotspot at your house, providing an area of coverage, and then you have multiple subscribers or client radios within that area of coverage connecting back to the access point. So often we see these used together, where you have a point-to-point network providing a backhaul connection for a point-to-multipoint network. So from this access point, you might have a backhaul point-to-point connection back to wherever your network location is, where you can jump on a fiber line or something like that. Or maybe you have one right at the access point, but that's not as common. So on the right here, this is a picture of a MikroTik point-to-point radios. So just dish-based, pointed at each other at a very long distance, creating a virtual wired connection between the two. So I wanted to talk a little bit about antenna types, because kind of once you get to know what these antennas look like, you start to see them all over the place. And these are used in tons of different applications, and they look the same across all of them. So here we're talking about a couple of frequency bands, 5 gigs, 24 gigs, etc. But cell radios and other radios at different frequencies, from 800 megs up to 10 gigahertz, they all look the same. So you'll start to see these all over the place, especially on cell towers. So the first and probably the most common type that you'll see is a sector panel antenna. They're these large rectangular objects. And what they typically do is a directional beam width that ranges from 120 degrees down to about 60. They can go a little bit. I've seen ones that are 40 or 45 degrees as well, but typically they're 120 to 60, something in that. And often they're used in an array to provide coverage in a 360-degree manner. So these are typically used with access point radios to provide coverage across a wide area. Then the second antenna type is omnidirectional. This is the more traditional type that's providing 360-degree signal radiation. So this again is used by access points. Somewhere central, if you wanted to say give internet to your cottage and you wanted an external antenna that would give long distance Wi-Fi coverage for your whole property, you would use something like this. And same thing if you were deployed in traffic or somewhere else. If you have subscribers that are going to be in all sorts of directions around the antenna, then it makes sense to use a 360 omni antenna. And finally, the other common type is a patch or a dish antenna. So the client, like the subscriber radios, typically use patch antennas. That's what this round one is. And that typically has a beam width of about 10 to 30 degrees, usually on the higher end, 20 to 30. And that just narrows in and allows you to go a little bit longer distance. So typically your access points have these wider spread areas to get lots of coverage, whereas the actual clients don't need as much and they're a little bit more narrow focused in. And then dish antennas look fairly similar, but they're even tighter, usually about 10 degrees of beam width. And that's what's used for those long distance point-to-point connections. And the purpose for that is, one, you're focusing all that energy in a little 10-degree slice. That's allowing you to protrude the energy much further than you would if it was spread across a wide area. And also you avoid a lot of the interference by only focusing in that one direction. So the more you transmit out, the more you can actually receive back in the way of interference. So by keeping that nice and tight, you can go a long distance and you can have a more or less interference that you would experience. So kind of what that means in practice, and I find this interesting. Once I learned this, I often look at cell towers now. It's kind of funny, but yeah, here's a picture of a standard 5G cell tower. And what you'll notice is lots of sector panels and lots of dish antennas. And that's usually what every single cell tower is made of. You'll see the occasional small omni antenna or something sometimes, but it's typically sections, sometimes multiple rows of these sector panels. So these are each, I think I counted around 9 of them around in a circle. So each one's probably got about a 40 or 50 degree beam width, slightly overlapping its neighbor. And that's providing local coverage for the cell service. And the reason they put multiple up is because you have so many subscribers in that slice, you have to kind of divide up the number of users across multiple radios because they each have their own limits. So this is the sector panel providing coverage around this tower. And then these dish antennas, these look a little different than this previous one, but it's the same thing. They just have this cover over top called the radome that kind of stops ice and snow from collecting in there. So same thing. Sometimes you'll see it be a flat radome, sometimes it's a dome. But what these are your backhaul connections. And so what this is likely doing is one of these is heading back to kind of the home network, link up somewhere, it'll jump on a fiber network somewhere. And then the other radio is providing a high-speed backhaul connection to the next cell tower. So often these are daisy chained together, where on one end you have a network connection, and at the end you stop at a certain point because after so many hops, the network connection is not good enough to really be shared. So you'll often see these. Sometimes there's a network connection at the base of a cell tower, in which case it will have 30 of these point-to-point radios because it's connecting, being kind of like the base station for a ton of different cell towers all around. But next time you're driving by a cell tower, take a look and you'll start to see these exact things, sector panels and patch antennas. But that's what they're doing. So in my blog, I also talked about the comparison between a WISP, which is a wireless internet service provider, and kind of a DIY network. And the reason I try to distinguish these two is because they're both using the same technology. So they're both still using Ubiquiti or MikroTik, Indian or other affordable radios, but it's more about who is actually deploying and maintaining the network. So in the case of a WISP, their job or their business model is to deploy and maintain a network in order to provide you, the client, a network connection at your facility. So all you do is pay for that connection monthly, and they take care of making sure that the radio network stays up, make sure the signal's good, make sure you're getting your internet, and you don't have to worry about it. So what I found going through this is that these WISPs are very regional. There are some national carriers, TechSavvy and ExploreNet, you're probably familiar with. There's also been a bunch of acquisitions recently, so Rogers, Bell, TELUS, they're all starting to get into this game. But often, a lot of them are very regional. Storm Internet is in the Ottawa area, NWIC is in the Niagara area, Targo is in Quebec, ICA Wireless is the one we use in the GTA. In fact, that's how we get our internet here at the office, because all we had was slow DSL available to us. So I highly recommend those guys. CCI Wireless, I believe, is based in Alberta, and Seaside Wireless is a big one out in the Maritimes. So if you want to find one local to you, what I'd recommend is use the keyword WISP and the name of the city that you're in, and you'll usually find some local players. As far as DIY, that's just deploying the network yourself. If you have infrastructure, you're a city or maybe a facility that has multiple buildings that you want to create networks between, this is you buying the equipment, deploying it, maintaining it, and operating the network yourself. So again, I'm focusing on Ubiquiti, but MikroTik and Cambium networks are quite popular options as well. So before we get into examples, I just want to talk briefly about kind of some design concepts that you should keep in mind if you're going to start trying out some of this network deployment stuff. I had started, when I was writing the blog, I started getting into actually explaining all the steps of design and realized it was getting way too complicated and way too long. So if you really are interested in this, I have my contact information at the end. I'd be happy to chat with you and provide you more information on how I do it. And yeah, I'd be happy to discuss that with you. But just in general, the key concept of connecting two radios together is line of sight. And that's really critical. Often people will forget about elevation changes. So when you're designing a connection and you're mapping out, the endpoints of your radio link, you really got to take into mind, you have to use a tool like Google Earth, or Ubiquiti has this cool kind of web tool that will do similar things to Google Earth, even a little bit more. And what it does is it can map out on a satellite image point A, point B, but the important part is that it shows you the elevation changes. So often it looks like even a road, if you're going a radio up a kilometer up the road, it might look like, hey, that's wide open, shouldn't be a problem. But if you look at the elevation profile, sometimes there's a big hill right in the middle that will block all your signal. So if you're not paying attention to that, you got crews out there trying to aim these antennas, it can be really frustrating because you'll never get it to connect. But if you don't know that hill's there, you're not going to understand why. So within Google Earth, if you create a line or a path on Google Earth, you can right click that and say show elevation profile. and it'll show you that profile, and same with Link UI. Same thing. So the big advantage of using a tool that's focused on wireless connections like Link UI is that they also focus and show you information on the Fresnel radius, or what I would always call the Fresnel zone. So when you're connecting these radios and you want line of sight, it's important to know that it's not like a laser beam. You don't want to just be able to see the radio, or if you see this obstruction, you don't want to say like, oh, I can get 1 meter above that, I'm good, these should connect. That's not how it works. Like when these radio waves are leaving the antenna, they're constantly expanding. So it's like a dome or cone of signals that's moving, that's getting bigger and bigger the further away from the radio that it goes. So this radio is creating this cone that's getting bigger, bigger, and this one's creating this cone that gets bigger, bigger. And the point where those two cones meet, that's where the data is being exchanged. I should have added a virtual kind of fuzzy line here, because the data is not getting sent at this visual line of sight dotted line. It's actually getting sent at many of the points along where these cones meet. So you need to make sure that that area is clear as well. And depending on how far apart, that could be anywhere from a meter around the visual line of sight, like a radius of 1 meter, up to a radius of 10 or 20 meters if you're talking about 10, 20 kilometers. So the ideal is to have that Fresnel radius completely free of obstruction, but typically it's recommended that at least 60% of that is free. So if you have this obstruction in the middle of your path, just because you're 2 meters above it from a visual line of sight, that's not often good enough. What you'll have to account for, and tools like this will show you what 60% of the Fresnel radius is at that point, and it's often more like 5 meters. So you just got to take that into account when you're going over obstructions. And one more thing I want to mention about elevation profile is that just shows you the ground elevation. You got to keep in mind that it doesn't talk about buildings or trees that actually sit on the ground and extend above that elevation. So often when you're mapping this out, if you see an elevation that comes close to blocking your signal, go to Street View or go zoom in there and take a look at what buildings or trees might be in there, because you have to account for that as well. And Google Earth is a good tool for that, because Google has all those 3D buildings mapped out in major cities. You can set the elevation height and look visually how that compares with the 3D buildings to see if you're going to go over top of a building or over top of a tree, or if it's going to block you. So I don't have time to get into those specifics, but again, if you want to contact me, I can show you very quickly in a couple-minute meeting on how to do that. But that's super important. And the other thing I wanted to talk about was paper surveys and real surveys. So when you're designing this network, you always want to map it out using one of these tools, figure out your elevations, check all these different things to make sure it looks like it will be able to connect. So you complete your paper survey, you validate it as much as you can on your computer, but then you can't just go out and deploy your network then and cross your fingers, hope it works. You have to do a real world radio survey. And what that means is taking 2 radios and going for each connection, mounting a radio, or you usually use a bucket truck on each side, put your radio up at the height you're going to end up mounting it, and try to aim it. Check your signal strength, make sure it connects, make sure there's no interference that's blocking you, make sure there's no obstruction you didn't anticipate, and record those readings. And you have to do that for every single link that you're hoping to do. And once you validate it with a real survey, then you can take that data, hand it to an installer, and say, here, it's validated, put the radios in these locations, and it will all work. So that's really the process you have to undertake, or you're gonna get in trouble with things not working when you deploy based on a paper survey. Now, if you're going super short distances, I'd say you can get away with it. If you have 2 intersections that are 200 meters apart, you can do it without a real survey. But if you're doing anything across any real distances above, say, 500 meters, I would always do a real survey. So now I'm going to talk about some applications and some real world case studies. It looks like I'm only down to 10 minutes, so I'm going to speed up a little bit here. So one thing that I don't see done in traffic, and seems like a kind of a very easy application, is kind of last mile sharing of internet. So what I've seen is when internet is deployed in a city, typically cities will run fiber down major streets. And so this is Bloor Street in Toronto. I'm just making this up. It just happened to have a nice grid location. So say that down Bloor Street, there's this fiber connections. At each of these major streets, there typically be a splice and a network switch in the traffic cabinet at each of these locations. So you could very easily, on one of those signal poles, put a radio and aim it up the side street. And by doing that, you can get signal at the very least, at least 500 to 1,000 meters up the street, and you could point it the other way as well if you wanted with a second radio. But by placing one radio there, and then here's another traffic signal, here's another traffic signal. So for a couple $100 it takes to buy the radios and the same to put them out there, you can share this internet and all of a sudden have your side street signals connected as well. So I think that's something that should be done, but it's not, I haven't seen it done very much. And as far as the radios I would use in that case is Ubiquiti Nanobeam are ones that I've used more than anything else. They're super affordable, very high data speed, and can go, you know, it depends on the conditions, but it can go 10, 20 kilometers, no problem. But in this case, in an urban environment like that, it'd probably go about 1 kilometer, you know, with obstructions and whatnot. But again, you can see for $500, you could set up those 3 signals, no problem. So these are more case studies we're going to get into now. So this is a project we designed and surveyed for the Highway 400. So the MTO was doing a large widening project on Highway 400 for the past 5 years, give or take. And so in about 2017, we got this work to kind of design a network and survey it. So what they wanted to do is have these camera poles online throughout the duration of the contract. They were planning to run fiber up here during that widening, but it wasn't going to happen until near the end of the project. So before the project started, they wanted to get connectivity to these camera poles somehow. And so they opted for a radio system. And so we went out and designed one and surveyed one. What we ended up doing was I put a sector panel antenna with about a 45-degree spread at this camera 1. That's where the fiber connection was. This is Google Earth, by the way, and this is the elevation profile tool. So I created this blue line, and then I just right-clicked it, said show elevation profile, and you can see here, there's no major humps between the start and end point. There was a little bit one here, so I highlighted that, zoomed in, saw there weren't any trees there, so it should be fine. But just as there's these big valleys that you see here, there could have been a big hill in the opposite direction, which would have caused problems. So what we did is we put a sector panel on one side. Because the road shifted a little bit, I didn't want to try to focus in with a dish and catch all these stations. And then on the other side, we used a dish antenna to more narrowly beam back to the access point radio. So each of these cameras look like this one on the left, and I believe they got about 50 megabits per second at each location, so lots of signal for a single camera. And as far as I know, it's been running smooth for the last 5 years. I believe the project ended last year, so I went by and it looks like the radios are taken down now and reconfigured somewhere else, but now it's running on the fiber. But a great use case. Highways are very wide. This is a 10-kilometer stretch of roadway for this point to multipoint, so we could have gone even further. We were, I think, probably about 14 kilometers is when the signal would have started dropping off for what we were looking at, but really easy, really cheap. And if you look at what we used a Rocket Prism, which is more of like the universal radio that you can change the type of antenna you use with. So this was the access point, a Prism, which is about $450, and then the antenna is about $150. And then the subscriber stations were these, I didn't change the name, but it's actually, I believe they were Ubiquiti Power Beam 500 ISO. There's a newer version of that now, but same concept, a dish antenna that has a narrow beam width as the subscriber station. So another application is very traffic focused, is traffic signal interconnectivity. So this is an example where we deployed a adaptive signal control system at a set of intersections. And in order for adaptive to work, the intersections need to be able to speak to each other. And the challenge here is that there was no existing city network to interconnect their signals. Sometimes you got a fiber or a whole network in place, and then that's great. But when you don't, it can be a challenge to implement one. So this system has been out there for quite a while, but instead of using radios, we had used, so this is a MyoVision system, which has a cell modem built into it with a SureTrack adaptive system running next to it. And so in order for this unit or all of these to talk to each other, we were using that LTE connection. So you're going up the LTE, back down the LTE to talk to this one, and vice versa the other way. And since these things are constantly talking to each other, we're using like 40 gigs a month on LTE to keep the system running. It just made no sense, cost a fortune. So what we proposed and put in here was a small wireless network. These are not long distances. I believe this is just over 1 kilometer here. And then these ones are a couple hundred meters themselves. So what we installed was a omnidirectional antenna at this access point on one of the traffic signal poles. And then we put one of those nano beam stations. So this is the master or the access point. There's the rocket prism with a omnidirectional antenna. And then each of the stations or subscriber radios had just a small nano beam pointing back at that location and connecting them all together. And they each got, I think, about a 40 megabit per second connection, more than enough than what we needed. And now they're communicating constantly, and we've just saved a couple thousand a month in these crazy LTE bills. So that's a nice, easy way if you want a small localized network. You could just have easily had a LTE modem here or a fiber connection or something that you wanted to share with your neighbors, and that would be a good use case for putting up a couple $100 in radios to share that connection. If you want to have basic connectivity to just be able to say change timing plans or get alerts for when controllers go into flash, you could use a cell network as a backhaul and then just get connectivity to each of those devices. So that would be a reasonable use case as well. So the final one I want to talk about is related to WISPs. And so this is a project where I ended up opting to use a WISP instead of developing our own network. So this client wanted to deploy cameras across a wide area. In this case, you can see it's about a 10-kilometer area. And at first, I was considering putting out our own Ubiquiti-based network across the entire corridor. But as we started surveying it, this section is not too bad. It's fairly straight, although there's quite a few hills. You can see here, this is quite a hill. But especially on this left side of the area, there's lots of curves and turns, and we found that we're going to have to put a ton of intermediate radios to build our own network, and it was getting very complicated. And so we found a local supplier, ICA Wireless, that actually had coverage towers in the area. And so working with them, they were able to supply an entire network connecting all of these devices together. I believe there was one tower somewhere up here in the top right, and then another tower somewhere here in the top left. And so kind of the ones on the left side connected to that tower, these ones to that one. And we got about a 10 megabit per second connection at each of these locations. So we were able to stream in 720p continuously back to our office and provide these video feeds to our client. So this is an example of where, one, we don't have a backhaul connection. So no matter what, even if we made our own network, we would need some sort of WISP or some sort of connection to backhaul. But two, it was going to get very complicated. So we ended up doing the math and finding out that providing a WISP connection at each was very affordable and provided us much more reliability on the network. So I'd say if you're going to be doing it yourself, focus on small networks like the last example I showed. And if you're going to want connections across a wide area, definitely consider a WISP. It's affordable and allows you unlimited bandwidth, which is the big distinguishing feature with cell modems. Now, some cities get cell modems with unlimited bandwidth now, and we're not that lucky, unfortunately, but if you don't have that, then I highly suggest WISP connections to get you high speed and unlimited bandwidth to run cameras and things like this. And just to show you kind of what these poles look like, it's just a camera on a pole getting AC power from a cabinet. So this is a cabinet we built, AC coming in, some power over Ethernet injectors to run the camera, run the network equipment. And so it's a camera on a pole and then a wireless dish antenna to connect back to the ICA data tower. Often they use cell towers or private buildings. They kind of deploy the radios creatively in order to get coverage across various areas. So that's it for that one. Oh, and I should have been telling you, I forgot to say at the beginning to pay attention because we will have a quiz at the end. So all of our webinars include a short quiz where we try to give away some goodies to the first person that can answer the question correctly. So this time we actually have these new Yeti mugs, so we're going to throw one of those in here as well. So you'll get these 4 goodies. So I'm going to ask a question, and then if you can enter your answer in the question box, I believe that's the only place you can enter text. But if you enter the answer as fast as you can, Samantha will take a look for who answers correctly first, and we'll announce it, and we will connect with you after the webinar and ship this stuff out to you. So here's the question. What are the most common antenna types used by subscriber/client radios? Is it A, sector panels, B, patch/dish, C, omnidirectional, or D, dipole Yagi? We'll see who gets that first.
So we do have quite a few answers already. The correct answer was B, and the first person to answer correctly was Lane. So I will contact you afterwards to get your shipping address.
Perfect. Well, congratulations, Lane, and thanks everyone for participating. So that's it for the webinar. We'll take some questions now. We have about 15 minutes left. So let me see if I can see the questions. I know sometimes I have problems with it. Omnidirectional, that's all I see. Sam, do you see questions there? I can't see any here.
Yeah, there's one at the top.
Oh, yeah. Can you deploy these radios in solar applications? So yes, you can. It's not ideal. The radios consume about 6 watts, I believe, is the typical for the nano beam. So you can do it, but just to support the radio, you need about a 200 watt solar system. And so depending on what else you're adding, it's probably going to consume a similar amount. So you're going to need a decent size 300 to 400 watt system. So you can do it, but it's a large solar system that you need to support it. And Sam, if you could just read them out for me, I'm not able to pull them up so easy there.
Yeah. Someone asked, is there a recording of this webinar? Yes, there is. Everyone who registers will get a link to the recording and the slide deck tomorrow. Someone asked, what is the maximum number of clients/subscribers that can connect to a single access point in the PTMP network?
Good question. So I believe the max limit built into the radios is 120 subscribers, but usually when I'm designing things, it's usually 5 or 10 at the most. But I know Ubiquiti usually says if you're deploying this as a WISP and you're trying to share a network connection, you want each of your clients to get about 30 to 50 megabits per second. So in order to give them that much bandwidth each, you want to limit the clients to about 50 per access point.
Someone asked, will Ubiquiti Radios work with other radio manufacturers' products?
No, they won't. So they kind of do and they kind of don't. So if you're creating a connection like point to point, you can't have Ubiquiti on one side and another brand on the other side. They have to be the same brand to connect. They can be different models of Ubiquiti. Mind you, they don't all interconnect, but a lot of them do. So if you, as far as the point-to-point connection, that they both need to be Ubiquiti. But if you wanted to have a Ubiquiti point-to-point connection, but then at the end of one side of that, you wanted to have it connect to an access point that's a different brand that would connect to subscribers that were a different brand, you could do that. So on a pole or wherever the two radios are, so say you have a point-to-point connection happening here, on this end, you would have an Ethernet connection between that radio and whichever other next radio you wanted to act as the access point or as another point-to-point if you're going to daisy chain to another one. They do interface through Ethernet, but wirelessly, they won't connect with each other. So same with point to multipoint. If you have Ubiquiti as the access point, all the subscribers would have to be Ubiquiti radios as well.
Someone asked, do trees affect the line of sight the same as a building?
Not the same. They do impact it, but it's less because there's a lot of steel, drywall, and much more denser materials inside buildings. They will block it almost absolutely, whereas trees are a little bit more forgiving. So yes, certainly going down roads. One thing I think I skipped a bullet point there, where roads act as really good line of sight corridors because they're usually very straight. They do work great for putting out networks. Mind you, there are lots of trees along corridors and roads as well, so that can limit the distance you can go. So sometimes you can get away with near line of sight, meaning there's some trees blocking, but not a ton. But the biggest thing to keep in mind is if you're doing a survey in the winter, you really need to be careful because those trees will not have leaves in a lot of cases. And so I'd be very careful if you're deploying where you can see bare trees that will have leaves in the summer because it will certainly block the signal significantly once they come back in. So I would suggest if you're going more than a kilometer, I wouldn't go through more than say 2 or 3 trees, and that's more going through the edge of the tree, not the bulk of it. If you're going through the bulk of a tree, it's going to block almost all the signal. So it's better than a building, but still does block quite a bit of signal.
Someone asked, can you place multiple radios on the same pole or will they interfere?
Yes, you can. You just have to set them to different frequency channels. So within each of those bands, the 5 gigahertz band has, I believe, about 27 different channels. So it's a large band, but the amount of bandwidth that you're using within the band is a smaller slice. So you just have to make sure that each radio is using a different slice so that they're not speaking on the same frequency band, the same exact frequency, or else they will interfere. But I know I've seen poles with 5 or 6 radios pointing in different directions, and they will absolutely work. But more typically, I only have 2, maybe 3 at the very most on the same pole, and usually it's because I'm changing direction. So I'm going down a road, point to point, and then I want to go down this direction. So I'll have a second radio now re-aiming the network down that way.
Someone asked, in your 10-kilometer example, what was the camera you used?
We didn't supply the cameras. I believe those are Bosch MIC cameras, but we weren't involved in that portion. We were just involved in the radios.
And I think that's the end of the questions.
Beautiful. Well, thank you everyone for attending. We do have another webinar coming up in 2 months. So that's going to be May 4th. Again, it's always the first Wednesday of the month at 1 p.m. And so MyoVision has released a new generation of hardware called MyoVision Core. And so my colleague Harrison and my colleague Zach from MyoVision will be presenting that. So when we send out our recording tomorrow, we'll include an invitation for this, as well as a few reminders along the way over the next month or 2. But I hope you guys will join us then. And here is my information. So my email is michael@stinson.ca, and there's my phone number. So feel free to give me a shout or shoot me an email, and I'd be happy to answer any questions or give you some advice on choosing a radio or helping with your design or reviewing a design that you might have in mind for a project. But thanks again, everyone, for attending, and hopefully we'll catch you on the next one. Bye-bye.